I'm not on the right screen. That video's up.
Give you $5.
You're recording the video.
I know.
Video.
I'm recording the video with the video. All right, so we'll do another buffer problem that's hard. This time we're going to start with a weak base. So this is that organic weak base. All right, we need a salt that contains that conjugate. So if I'm telling you this is a weak base, what does it have to do has to gain a hydrogen. So this is okay. All right. So this is the weak base. This is its conjugate. So I need a salt that contains that conjugate acid to be put with it in our problem.
If it's a weak base, how come you can put the double arrows?
If they're weak anything, I should be writing double arrows on all of them because it comes to equilibrium.
Is it the strong ones that you don't?
Right. The strong ones you don't. You write only because we assume they dissociate completely. So then that's why it's a stoichiometry thing and it's a one arrow.
Wait, so it's an equilibrium if it's on the reaction side if it's a weak base.
She's asking about this double arrow. Yeah, it's double arrow equilibrium if it's a weak acid or a weak base.
So is that only on the reaction side, or?
What do you mean on the reaction side?
Like, does it matter what side it's on?
No. You mean which side the acid or base is on?
Yeah.
Yeah, no, it doesn't matter. No. Okay, so we need a salt that contains that conjugate acid. So give me a salt and give me a concentration. Buffers have maximum capacity of buffering when those concentrations are the same, by the way. So you want to do one where they're the same? That's where they have the maximum buffering capacity, is when the conjugate has the same concentration as the... its ability to buffer. Like eventually I will put in so much strong base into the one we just did that it will become basic because I will go over the buffering capacity of the buffer. Okay. Basically, I will stoichiometrically use up all the acid. Okay. So, and it becomes, just like you said, the acid is now not the limiting reagent, the base is. The other way around. The base is no longer, the OH minus would have been no longer the limiting reagent, the acid would have been, and we would have had leftover OH. So we have exceeded the buffering capacity then. So, okay, so that went back to the other problem. All right, so we need a salt. Pick a, you want to pick K instead of Na since we always pick Na? Okay, so we have a salt that contains the conjugate of the weak base. So now we know we have a buffer there. Even if they don't tell you in the problem that there's a buffer solution, you should recognize that there's a buffer because there's a weak base with a salt with its conjugate in it.
Should it be NH3?
Yeah?
Yeah, essentially.
Wait. But if you have a K and then the charge does not add up.
Yeah, because the K's... Oh! Lord. Did I do it backwards? Did I do...
No, I'm confused.
No,
I'm sorry.
Just erase that cane.
Should it be?
Did I just lose my train of thought? Hang on, you messed me up. All right, wait. This is our weak base. This is our conjugate acid.
You can't add.
We need, yeah.
Do you have to start with an acid, weak acid, and go to?
No, I was just trying to do, no, you don't. And that's what I was doing, I was doing it the other way. Yeah, I added a cation to a cation. We can't do that. So we have a cation.
Okay, here we go.
Right. So we need an anion. What would be the better choice to put right here?
Bromine.
Not OH. Bromine or Cl. Right. Sorry, good catch. That means you really get it. Good catch. Sorry about that. All right. So the cation, the conjugate acid cation, needs an anion from a strong acid so that it doesn't affect the pH. All right. So here's our buffer. Okay. Then we are going to add a strong acid to it. So let's add 0.03 moles of HCl. So you have a solution that contains 0.4 molar methylamine, this thing, and 0.4 molar that bromide. I don't even know what that anion's called. And you're going to add to it 0.03 moles of HCl. Okay, what are your major? You want me to do it with you? Or you want me to let you work?
Do it with us.
Let's work.
All right, you work. I won't talk. I'll just write. How about that?
Yeah. Okay.
Do I need to freeze the screen so you can't see it?
No, keep
Just keep going. Okay. Uh-huh.
why is the okay? If in the solution we have that concentration of CH3 and H3Br, then why is that not one of the species in the solution?
Because this is a salt, and we're going to make the assumption that it's a soluble salt. And so if it is a soluble salt, then it exists in solution because it dissociates 100% into that. Mm-hmm.
How come OH
There is, where is it? This is what I put in the solution. This is what I'm putting in the container.
Oh.
There's not any OH there.
So how come you wrote it in the equation?
Ah, I was just showing you the dissociation of this weak base so that you would catch what the conjugate acid is.
So
This is not the equation we're going to work with. I was just trying to show you because we picked that weirdo base. I was just trying to show you what that conjugate acid would look like. So we don't need that right now. Okay.
Does WB stand for
Does what?
Weak base.
Weak base.
Oh yeah, WB, weak base. Yeah, sorry. That's me scribbling.
okay.
All right, we got to decide
Why
what,
did we cross out the
because they're not going to affect the pH because they are conjugates of strong acids. So they're not going to affect the pH. So we crossed them out.
Do we know the K thing?
Oh, we do not know the K thing. You're right. Somebody's got to look up KB for us. Sorry. Will you Google that? Somebody? Of the weak base of the CH3 and H2, the methylamine. Okay, you're right. That should have been given in the problem.
can you know what the base is in the weaker species?
Yes, you
Like,
need.
you need to figure that out.
Yes, you need to recognize that. Right. The thought process in your head should have been that this is a strong acid or it's just an H plus. This is a weak base. This is the conjugate acid of that weak base. I don't care about these two because they're conjugates of strong acids, and then there's water.
And this is all
That's
one-
kind of the thought process I went through with those major species.
this
Yeah.
is all 1 liter solution.
We didn't specify. We didn't specify. Does it matter?
Yes.
You add moles of
Okay, so let's pick a. Do you want to pick something other than 1 liter?
Yes. Oh.
2.
Well, I mean, it'll make your math harder, but you'll see it.
We need to know how to do it.
We need to know how to do it? All right, so we're going to pick 2 liters?
Yes, please.
All right, so then we'll pick 2 liters of solution.
We need to know how to do it.
2 liters
All right, so we'll pick 2 liters of solution. All right, so we have to do stoichiometry. This H plus is going to react with this weak base first and completely. So that's why it's stoichiometry. It's hard. It is hard. I'm not going to get it. It's hard until you start to recognize some of this.
How long do we have until you have to go?
About 10 minutes. So I got to go fast. Okay, I'll write fast.
Okay.
Okay, it's not really ice. It's really F, right? Because we're doing stoichiometry.
Then why did we write ice?
Because I wrote final there. I cheated. Okay. Because it's just faster than doing stoichiometry with factor label. This is faster. So I do these in moles. Okay. That's what we did.
Table though. We just do stoichiometry.
Well,
right?
then you go right ahead. That's going to take forever. I'm doing it in a table.
Okay.
All right. So I know I have 0.03 moles of, oh no, does this, no, we're okay, aren't we? All right, 0.03 moles of H plus. How many moles of the
Moles
weak
over
base do I
two.
have?
But we need it to
Let
be
me put it
more.
in the
Similarity at the
similar.
top, so-
Yeah, so we have 0.4 molarity and we have to multiply it by 2 liters. So we have 0.8 moles of this.
Why didn't we do the molarity?
Why didn't we use the top equation?
Don't we usually do
too many
concentration
questions.
on the table?
Okay, 5 different questions at the same time. One question was, why did we not use this? Because our major species have a strong acid with a weak base. This is going to react first, then we will shift back to equilibrium of that weak base. This is the hard part. So we had a weak acid added to a buffer. So that's why we're not using that equation. We are doing the stoichiometry of the strong acid reacting with the weak base completely first. All right, what was your question?
First of all, you just said you added a weak acid to a buffer, but I thought this whole thing was.
I mean, strong acid. Did I say a weak acid? I don't know what I said. A strong acid to a buffer. This was a strong acid to a buffer. So what's going to happen first is the H plus from the strong acid is going to react with the weak base, right? With the weak base first and completely. And this table, this stoichiometry, we are going to do in moles. So we had to do molarity times volume to get moles of the base.
Do we not multiply the H
Oh,
plus
shoot.
moles by 2 because it wasn't in the solution in the first place?
But it's moles. So it doesn't change the liters, and we already have the moles. So that's why that's going straight there.
But we always use molarity in ice tables.
Correct.
do we not?
Correct. But this is not an ice table. This is a ICIF. I don't know.
It's
This is an ICIF table. This is a stoichiometry
So
table.
Ice tables use molarity. Ice tables.
Sure.
Ice tables use moles.
Moles. Correct.
Okay.
All right. We have a concentration of this too. We have moles of this. This is also 0.8 because it's 0.4 times the 2 liters. So this is also 0.8 moles. All right, so now I'm thinking through stoichiometry. Instead of doing factor label mess, it is faster because these are 1 to 1 to 1. Which one of these is the limiting reagent?
H plus.
H plus. So it's going to get all used up. If I use 0.03 of that, I have to use up 0.03 of this, and I have to make 0.03 of this because they're 1 to 1 to 1, right? So now my final molarities, this one's going to go to 0, this one's going to go to 0.77, and this,
She subtracted.
right? Did I do it wrong?
No, you're right.
Why did you add
This is-
Oh, right.
Okay.
Okay, that would take you 3 stoichiometry problems if you did it, right?
this is-
That's why I'm doing it in table. All right, so this is moles. Now what's left? What are our major species that are left now?
CH3NH2 and CH3NH2 plus.
Okay, let me write that down. You said it faster than I can write it. CH3NH2, CH3NH3 plus, and what else?
Just
The water. And really, technically, Br minus and Cl minus are there, but they're spectators, so we don't care. What do you know now? What can you tell now? New ice table. It's an equilibrium problem now. It's either a weak base problem, common ion problem, or if you recognize it, it's a buffer. So we can use an ice table, or we can use Henderson-Hasselbalch at this point.
I don't see Hasselbalch. Because we'll leave.
No, no, no.
You don't recognize the buffer. It's,
He's like
again, here's the
anti-buffer.
weak base and its conjugate. It's a buffer. That's what's left. All right, so let's do it in an ice table just to stay consistent. Now we're going to worry about this weak base dissociation.
What are we trying to find? with
The
all
pH.
this
pH.
work? Is it worth it?
It's just done. It's just like, nope,
And
not
you
worth
should
it.
have asked that class before you signed up.
Yeah. It may not be, but this is how you have to do it. I'm just going to leave that one there. All right, so this is now our equilibrium ice table. And now we're going to stick in molarities, not moles. So Our moles of this, oh gosh, I can't remember. What did we have? 0.77 moles of this. But how many liters is it in? So I need to do that math. We don't care about the H2O because it's a pure liquid. This was 0.83 moles. Again, it's still in 2 liters of solution, and this is 0. So somebody do our math for this so I can write out the number. What's 0.77 divided by 2? 0.385 molar. And what's 0.83 divided by 2? Point what? What? Okay, that makes more sense.
Yeah.
Oh, 183.
Okay, I was like, that makes more sense. So that's the molarity of that one. All right, which way is it going to shift? To the right. So minus x plus x plus x. So 0.385 minus x, nope. 0.415 plus x, thank you. And then x. And then KB, which we looked up was, what did you tell me? 10 to the negative 4. Okay, so 4.4 times 10 to the negative 4 is going to equal 0.415 plus x times x over 0.385 minus x. What are we going to assume about the plus and minus x? We don't need them. And then we're going to solve for x, and somebody's going to tell me what that is. Y'all are too frantically writing. I don't know. 4.08 times 10 to the negative 4th.
4.08
Yeah, because these are very similar, so that makes sense. So then the pH is, that is the H plus constant. No, it's not. That is the OH minus concentration. See, and that you'll make that mistake too, so pay attention. So the POH is the negative log.
Red TI-84.
Oops, negative 4. So what's the POH? Just to make that stop.
So the pH is 14 minus. The answer is 10.6.
3.39.
Okay, so we'll just call it 3.4. And then the pH then is going to be 14 minus that, which comes out to be what? 10.6? Whoops, that didn't make very well in the end.
So what is this the pH of?
That's the pH of a solution that contains everything in that box.
Right. Gotcha.
So it's got HCl, it's got this salt, and it's got that weak acid.
The answer is what?
10.6.
So John, you said that 9 out of 10 would be about like finding the pH. What would the rest be like?
Like, what's the conjugate of this? What's the conjugate of that? What's the you could be able to
The Bronson-Lowry base.
yeah, definitions of the Arrhenius and Bronson-Lowry stuff. The Lewis acids and bases is not on there because they took that. That's part of the complex ion stuff with the Lewis acids. You see it better. That's all off.
So we do have to know like what would be erroneous acid and constant.
Right. Right. You need to know the difference in
Probably
definitions.
some
Uh-huh.
increase
So in
in
terms of like chapters and sections in the book,
It's all of chapter 16, and it's 17:1 through. I want to say. No, we've done more than that. I think 3 or 4. Let me. Oh, this is the old book. I think the sections are the same though.
18.34.
I'm looking. It's not the titration. It's not. It is just through 17.2. It's 17.1 and 17.2. Yeah. Yeah. So all of 16, 17.1 and 17.2. And what we did, everything that was new to you today was 17.1 and 2. So really, huh?
The Bronson-Lowry one is the one that just says as long as it takes the hydrogen.
It's the donates and accepts
Yeah.
protons, where the Arrhenius says it has an H plus and OH minus. So they get more inclusive, right? When you looked at the Arrhenius definition, it had to have an H plus or it had to have an OH minus.
Like in
So
the
like
formula.
the NH4
in the
bases.
formula.
Okay.
Right. So then when you get to NH3, well, I can put litmus paper over that and over ammonia and it turns blue. So it must be a base. So how do I explain that? So then the definition broadened, right? So the Bronsted-Lowry definition was if it can accept or donate a proton, which is really just H plus. Accept or donate a proton. Right, because if you think about a hydrogen atom, how many protons does it have?
Has one proton.
How many electrons does it have?
Has one.
And how many neutrons does it have?
I think
Zero.
0.
So if I strip away the electron to make it an H plus, what's left? Nothing. That's why sometimes it's called a proton, and that's why you see protic acids, polyprotic acids, right? That kind of
Wow,
thing.
You just memorize.
So for polyprotic acids, I remember there were like questions on like they would give you like a series of K values.
Yep,
For each of the which ones do you use for what
the first one.
every time?
So yeah,
Okay.
the polyprotic acids mean it has more than one H. So, and this one's weird. We won't even comment much about that one. But H2SO4, H3PO4, H2CO2 through CO3, right?
Right.
Those are polyprotic acids. They have more than one H. So when you look up K values, and we're going to ignore this one because this one's really a strong acid, but then its second one is a weak acid, and this one's just special. So let's look at these two. So if you had H3PO4, these H pluses come off one at a time. So if the first H plus comes off, we are left with that. That dissociation is Ka1.
Right.
The next H to come off is Ka2. The last H to come off, I'm gonna close it there. PO43. This is Ka3. It will always be that Ka1 is bigger than Ka2 is bigger than Ka3. Because once there's so much H pluses in the solution, is this thing going to want to shift this way as much? No. So if you have to do the pH of these, you can do the pH just based on Ka1 and
So, like,
basically ignore the shifting for 2 and 3.
We're never gonna get like buffer questions and ask.
Oh,
it's all,
no,
like,
no.
Accurate.
No,
Okay.
you're not going to have that. You could be asked to find they list all the Kas of these, and they give you a concentration or something, but you're just doing it off the first Ka. You just use the first
So
Ka.
technically, like all of like HPO4, H2PO4, H.
They're all technically weak acids.
And they're all gonna be present in the solution.
Depending on how much OH is there. Yeah.
Uh,
Depending. Well, and this one shifts, and then that. Yeah.
okay.
To some extent. Uh-huh.
So is NH3 kind of like water in that, like if it gets another hydrogen, it can be acidic, and if it's NH2,
No. NH3 can only make NH4 plus. That NH2 on that organic acid or organic base, it's a different group than this. It's an amine group, right? So it's different.
So, but it signifies that it's basic.
Yes. This thing is technically not amphoteric like water, amphiproduct, what do they call that word? But this one can function as a weak acid, but it can also function as a weak base. Why can that one function as both? Because it can go either way, right? It can go this way and it's functioning as an acid. If it's here and it's going that way, what is it functioning as? A weak base, right? Because it's gaining
So really those
H.
arrows can go back and forth.
So, right. So these right here can go back and forth. This one though, can that?
They can't go forward.
It can't go forward. It can only go the other way. Right. So,
If strong acids and bases are the ones
I'm
that-
assuming that means you move. All right. I'll save this one too. I'll put them on YouTube.